Previously, we've been discussing intermolecular forces, solid state chemistry, and the hard sphere model to predict density for both metals and ionic salts. So in this lecture, we're going to continue on with our discussion on solid state chemistry, but today we're specifically going to focus on band theory. And band theory is a little bit more sophisticated approach for talking about bonding for solids. So we'll talk about band theory for conductors, insulators, and semiconductors and how those three different types of materials vary. We'll discuss doping of semiconductors to increase the conductivity, and we'll talk about both p-type and n-type doping, and also applications of p-type and n-type doping. We'll talk about light-emitting diodes, such as these over here, as well as solar cells. Before we can talk about band theory, I just want to give a brief reminder of the metal-nonmetal line. So this is the upper right-hand corner of the periodic table, and we have this metal-nonmetal line that's cutting the p block, and elements that are to the top right of this line are nonmetals, and elements on the bottom left are metals. Elements that are along this line, such as silicon, germanium, arsenic, etc., these are considered metalloids or semimetals. So metals are conductors, nonmetals are insulators, typically, and metalloids are semiconductors. Previously, we introduced the sea of electrons model to describe metallic bonding. And in the sea of electrons model, what we said was that since metals have low first ionization energies, these metal atoms are ionizing, so that these positively charged spheres are representing the metal ions. And then we have this sea of delocalized electrons that are holding together all of our metal ions. And these sea of electrons are delocalized over the entire array of metal atoms. So we want to introduce a little bit more of a sophisticated approach for describing bonding for metals, and this is using band theory. So band theory is just an extension of molecular orbital theory. So we've talked about molecular orbital theory back in Gen Chem 1. And in molecular orbital theory, what we say is that our atomic orbitals mix to form these molecular orbitals. Molecular orbitals So molecular orbitals are delocalized over the entire molecule, or in this case, we're talking about a solid. And so what we're looking at here, if we thought about two lithium atoms coming together, our two s orbitals would mix to form our sigma bonding and antibonding, and then our sets of two p orbitals would form our pi and sigma bonding and pi and sigma antibonding. When we start adding more and more lithium atoms, so here we have 4 lithium atoms, now we have 2 sets of 2s bonding orbitals and 2 sets of 2s antibonding orbitals. And as we continue to add more and more atoms, what will happen is we will start creating a band of orbitals. So free atoms have these discrete energy levels, but in solids, since we have so many different molecular orbitals that are being generated from all of the different atoms, imagine if we have Avogadro's number of lithium atoms, that what ends up happening is we end up creating bands. So we have what's called our valence band. And our valence band is just simply our lower energy molecular orbitals that are occupied by electrons. And then up here, our empty orbitals is what we call our conduction band. And the conduction band simply are the higher energy molecular orbitals that are empty. And the ability for electrons to occupy the conduction band determines the conductivity. So we just mentioned that the ability for electrons to go into the conduction band determines the conductivity of the material. So the conducting properties of a substance are determined by this energy gap between the valence and conduction bands of the molecular orbital. So you can see from these pictures that for a conductor, we have no energy gap between our occupied molecular orbitals and our empty molecular orbitals, so our valence and our conduction band. Go all the way over here to an insulator, we have a very large energy gap between our valence and the conduction band. Semiconductors are somewhere in the middle. They have an intermediate gap between the valence and conduction band. Okay, so let's talk about how this affects the properties. So with a conductor, again, there's no gap between your valence and your conduction band. Electrons flow when a tiny electrical potential difference is applied. And something else that's important about conductors is that when your temperature increases, the conductivity actually often decreases. And this is just because you have introduced some random motion into your array of metal atoms. But conductors have very high electrical conductivity, and they also have interesting properties such as luster. So luster is this shiny property that we associate with metals, and this is just because we have so many energy levels that are so close together in energy. This luster property is just from the fact that we have all of these energy levels that are very close in energy. So electrons can be excited by absorbing photons, and photons can also be reflected off. And this is what gives metals this luster property. So some examples of conductors are metals such as silver, gold, copper, etc. Semiconductors, like we mentioned before, have a small energy gap between the valence and the conduction band. And with semiconductors, thermal energy can excite electrons across that gap. So as you increase the temperature, the conductivity increases. And some examples of semiconductors are silicon and germanium. Finally, we have the insulator. So with an insulator, we have a very large energy gap between our valence and conduction band. And insulators have zero conductivity. There's no increase in conductivity when the temperatures increase, and that's just because this energy gap is so large that not even an increase in temperature will increase the conductivity. Diamond is a great example of an insulator. It has a large band gap. So here's just a quick figure of the difference in band gap between diamond, silicon, and germanium. So germanium is actually a little bit better of a semiconductor than silicon. It has a higher conductivity because it has a smaller band gap. So pure silicon is actually not that great of an electrical conductor at room temperature, but we can increase the conductivity of silicon by doping silicon with small amounts of impurities. So silicon can be doped. So we need to talk about both p-type and n-type doping. So with a pure silicon crystal, like we mentioned, there's an intermediate energy gap, and it's not that great of a conductor. Okay, so we first need to introduce n-type doping. And this N simply stands for negative. So with n-type doping, you're introducing an impurity that has one extra electron compared to the silicon. So for example, if you look on our periodic table or this little cutout of the periodic table, silicon has an atomic number of 14, phosphorus has an atomic number of 15, neutral silicon has 14 electrons, neutral phosphorus has 15 electrons. So if we dope phosphorus into our silicon array, then we're basically introducing electrons into this array. So that's why we call it n-type doping. And I want you to think about what this energy gap looks like, or this band. So when you introduce extra electrons into the silicon array, you're essentially populating electrons into the conduction band. So phosphorus occupies some of the lattice sites in the solid silicon. And since phosphorus has one more valence electron than silicon, these additional electrons must enter the empty orbitals in the conduction band. And this will increase conductivity. Alternatively, we could introduce what's called p-type doping. And here P stands for positive. And in p-type doping, you want to dope an atom that has one fewer electrons than your element that's making up the lattice. So again, if silicon is our semiconductor that we're doping, gallium has one fewer valence electrons than silicon. So we can dope silicon with gallium. And now what this does, you could think about holes being introduced into the energy gap. So gallium occupies some lattice sites, which you can see here. And gallium has fewer electrons, creating holes or a positive site. Essentially, we're introducing empty orbitals. And so again, this is going to increase the electrical conductivity because it's going to be easier for electrons to be excited from this valence band into these holes. We also need to introduce a concept called a p-n junction. So a p-n junction is you've got a p-type semiconductor and an n-type semiconductor that you combine together. You can imagine this scenario. So you've got your p-type that has a bunch of holes or positively charged spaces in the lattice, and your n-type that has a bunch of extra electrons. So if you were to connect a battery up to a p-n junction in this way, the negative electrons would flow towards the positive or towards the p-type, and the holes would flow towards the n-type. And when we get a combination of a hole and an electron, energy is released in the form of light. So let's talk about an application of this p-n junction. So that first example that I had mentioned to you, if you set the positive type, the p-type is hooked up to the positive end of the battery and n-type is hooked up to the negative side of the battery. Again, what's going to happen is you're going to get your electrons are going to flow towards the positive. Holes are going to flow towards the negative. So we're going to get electrons and holes combining. So what you can think about is you have these electrons in the conduction band. When they combine with a hole, essentially this electron is relaxing down into a lower energy state that's essentially the width of that band gap, that difference in energy. So when the hole and electron combine, basically the electron is relaxing to lower energy. Light is released because we have conservation of energy. So light's released and we get an LED light. Solar cells are an example of this p-n junction. So when you first put together a p-type and an n-type semiconductor, you get combinations of your holes and electrons, and you create this depletion zone. And in this depletion zone, you have electrons and holes. So for example, if we have phosphorus as our n-type dopant and boron as our p-type dopant, the electrons on the phosphorus have transferred to the boron, creating positive phosphorus sites and negative boron sites within the depletion zone. And when a photon hits the solar panels, so if you have a photon coming in, an electron can be knocked free. And this creates a free electron and a new hole. And this causes a buildup of energy, which essentially forms a current. So solar panels are another example of an application of semiconductors. A great illustration of band theory are two of the primary allotropes of carbon, diamond and graphite. Because of their different structure, they have very different properties. So in diamond, we have these sp3 hybridized carbons that are all in this tetrahedral structure. So in diamond, the electrons are localized. We don't have very much delocalization at all. So the electrons are just between the two carbon atoms that they're holding together, basically. Because of this localized electrons, remember we talked about how things that are conductors have delocalized electrons. Materials that have localized electrons are going to be insulators. So there's a large gap between our valence and conduction band for diamond. Graphite, on the other hand, we have all of these p orbitals. So it's sp2 hybridization on these carbons. And there is a p orbital on each one of these carbons that is not involved in hybridization that can form these huge delocalized pi molecular orbitals. So the electrons in graphite are delocalized because the electrons can spread out over the entire sheet of carbon. So this is going to allow overlap between the conduction and valence band. So graphite is a conductor, diamond is an insulator. You can also understand the difference in color with band theory. So diamond has a band gap that is too large to absorb visible light. Whereas graphite, many wavelengths of visible light will be absorbed. And so that's why graphite has this black lustrous color, whereas diamond is colorless. So one exception, though, there are some colored diamonds. One very prominent example is the Hope diamond. And we can also understand the color of the Hope diamond using band theory. So the Hope diamond has boron impurities. So boron has one fewer electron than diamond. So essentially, it creates holes in the diamond structure. So we essentially have these boron acceptors, and you can excite an electron from the valence band to the boron acceptor with red and orange visible light. So boron defects lead to a hole or a lower energy level in the band gap. So diamonds with trace boron can absorb red and orange light and appear blue. Hopefully you've seen some of the many different ways we can use band theory to understand solids, such as semiconductors and their roles in solar energy and LED lights, and the color of the Hope diamond.